Welcome to Math with Professor V. In this video, we're going to learn about improper integrals. So what exactly are they? How many different kinds are out there? And how do we evaluate them? I'm going to answer all those questions and more in this video and work through plenty of examples for you. That way, by the end, you'll be ready to tackle your homework exercises or whatever other improper integrals you might encounter during your calculus class. So first things first, let's talk about what exactly is an improper integral. And we have two main kinds. We're going to focus on one particular kind first and work through some examples, and then I'll move on to the second type. So we're going to call the first kind a type 1 improper integral, and the definition is as follows. So if the integral from a to t of f of x dx exists for every number t greater than or equal to a, then the integral, now this is the new part for you guys, from a to infinity of f of x dx equals the limit as t approaches infinity of the integral from a to t f of x dx, provided this limit exists as a finite number. Now, I know when you read a math definition, in the beginning, they are super overwhelming, and if you end up being a math major, you get over it, sort of. But let's just focus on this part right here, because this is going to give us our definition, which lays down the process for how we evaluate these improper integrals that we encounter. So when you have an integral that goes from a to infinity, what makes it improper is the fact that the upper limit is now infinity, right? It's not some other constant. Usually we go a to b, right? That's what you've seen up until now. Well, what we do is we say these are equal, and we redefine, we replace infinity with some new dummy variable. Usually we use t, okay? And then we take the limit as t approaches infinity instead of having an infinity up here. And then we go ahead, evaluate our improper integral the way we normally would, evaluate it at the limits of integration. You're gonna have a bunch of t's left over, and then you take the limit. Now these are equal provided this limit exists as a finite number. So as long as the limit is some finite number, not infinity, not negative infinity, or does not exist, then we say this improper integral is equal to the limit as t approaches infinity, a to t f of x dx. Good? I know it's a lot. Once you get the hang of it, you'll feel a lot better, okay? Don't go into meltdown mode. You guys got this. And then similarly, it doesn't always have to go to positive infinity, so that's what this little second part of the definition is. If the integral from t to b of f of x dx exists for every number t less than or equal to b, then look what's going on here. Obviously, you're going to have negative infinity as the lower limit always, right? It wouldn't make sense for it to be an upper limit. So integral from negative infinity to b f of x dx equals, again, now we've added in limit, t goes to negative infinity, and then we replace the negative infinity with t, and then now we have this limit out front. So these are equal, again, provided that the limit here exists as a finite number, okay? And then just some additional terminology that we use to classify improper integrals, and these might be new for you. We say that the improper integrals, either from a to infinity of f of x dx or negative infinity to a of f of x dx, these guys, we call them convergent if the corresponding limits exist as finite numbers. And then we call them divergent if the limits do not exist, or if the limits go to infinity or negative infinity. And you're going to want to remember these terms, convergent and divergent, because they're going to come up again in the sequences and series unit. Okay, so make sure you put them somewhere in the brain that they won't slip out the minute you finish this section. Okay, fabulous. Now, there is one other kind of type 1 integral where you have both negative infinity and infinity as your limits of integration. So how do we deal with that? Well, here's our definition part C, third little scenario. If both the integral from a to infinity and negative infinity to a of f of x dx are convergent, so both these guys have to be convergent, then we define the integral from negative infinity to positive infinity of f of x dx to be the integral from negative infinity to a f of x dx plus integral from a to infinity f of x dx, where a is any real number. So basically, as long as both of these integrals are convergent, meaning that when we evaluate them, rewriting them as a limit, we get a finite number, then this improper integral from negative infinity to infinity can be rewritten as the sum of these two integrals. And a, you get to pick, okay? So we'll work through some examples where we're going to look at each of these kinds, A, B, and C, and then see how to tackle them. Do you guys feel ready? Probably not. I wouldn't if I were you, but don't worry. I'll lead you through this. You got this. Okay, example 1. This is often how the directions are going to be. Determine whether the integral is convergent or divergent. Evaluate it if it is convergent. So they want you to say what the limit is, basically. Okay, here's the process. I would know it's an improper integral even if they didn't tell me, because I'm looking and I see that the lower limit is negative infinity. Yeah. So what do? Immediately, just be like a little math robot and you go, I'm going to rewrite it with a limit in the front. And then you introduce your little dummy variable. We usually use t. So the limit as t approaches, what's making this integral improper? This negative infinity down there. So that's where t is going to need to go. And then now I rewrite this as the integral from t to 1 of 1 over 2x minus 5 dx. How was that? Not too painful, right? That should be the very first step that you do anytime you see an improper integral. Now from here, just make sure you keep rewriting lim every step of the way, and then we're just going to evaluate this integral. So 1 over 2x minus 5. You can u sub if you want, but then we have to change our limits, right? So I'm just going to kind of work through the u sub in my head. If I had let u equal 2x minus 5, du would be 2 dx. So then 1/2 du is dx. So all that's going to happen when I take my antiderivative is I'm going to pick up a 1/2. And I know antiderivative of 1 over x is natural log absolute value of x. So I'm just going to have natural log absolute value, all this stuff. If I lost you, then just do the u sub. But I think at this point you guys have done enough integrals that you don't need to. So I'm going to write this as the limit. T goes to negative infinity. Don't forget, we've got that 1/2 ln absolute value 2x minus 5. And then this is going to get evaluated t to 1. And then at the very last step, we're going to put the limit. Or we're going to evaluate the limit. Okay, so we've got limit. Keep rewriting it. T goes to negative infinity. Let me take the 1/2 out. Okay, if you have a constant, you can always pull it out. That way it makes evaluating everything a little bit easier. And then I'm going to have natural log absolute value 2 minus 5. I'm plugging in 1, the upper limit, minus natural log absolute value 2t minus 5. So this isn't going to be a constant, right? This is a function of t. Okay, let's see what's going on here. So we have limit t approaches negative infinity 1/2 times. This is going to be negative 3, but then I take the absolute value. So natural log of 3 minus natural log absolute value 2t minus 5. Ooh, so how do we evaluate that part of the limit? Well, let's think here. As t goes to negative infinity, 2t minus 5 is also going to go to negative infinity, but then I'm taking the absolute value of it all. So then really all this stuff is going to positive infinity. So if this is going to positive infinity, where's natural log going? Think back to your graph of natural log of x. Do you have it burned in your brain? I hope so. If not, now's the moment to do it, okay? Because there's no other way to figure out the limit. Ooh, that's looking ugly. Hold on. Much better. Here's a very, very rough sketch. Y equals natural log of x. It goes through 1, 0, and then we've got a vertical asymptote right here. Boop, 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 boop. The important thing to notice is, okay, if the input, if your domain is approaching positive infinity, where is natural log going? So x gets very, very large. Where's natural log going? It's approaching positive infinity. This whole thing right here is approaching positive infinity. Okay, so what's going on? We've got 1/2 times some number minus infinity, right? This is just scratch work. This is like not official. Just so you can kind of put everything together in your head. Some number minus infinity, this is going to go to negative infinity, times 1/2, it's still going to negative infinity. So then our limit, I mean, I would hide this because this is a little embarrassing, but I think it's helpful, okay? Then you can say your whole limit is negative infinity. All right, what does that mean for us in terms of this improper integral? Well, the limit does not exist as a finite number. So this improper integral is divergent. And that's it. Okay. Let's box that. Don't forget to write it either. That happens sometimes. You're so excited you finished the limit. All right, let's look at more examples. You're not going to be an expert after doing just one, okay? So don't feel badly if you're like, I don't understand what's going on yet. It's fine. Determine whether the integral is convergent or divergent. Evaluate it if it is convergent. Same directions. Okay, so we have integral from 0 to infinity, x over x squared plus 2 squared dx. Very nice. Okay, so boom. What's making it improper? That infinity up there. So let's rewrite this now as the limit. As t approaches infinity, integral 0 to t. Very good. And then you have x over x squared plus 2 squared dx. Okay, so now how do we evaluate this integral? Well, look at the denominator. It has x squared plus 2. X squared is 1 degree higher than the numerator. So again, I want you to imagine that we're doing some u sub, that you have u equals x squared plus 2. Then du would be 2x dx. Very good. Which I almost have. I just have x dx up there. So 1/2 du would be x dx. Now, if you want to actually go through and do the u sub, you're going to have to change your limits of integration. So sometimes for improper integrals, I just imagine and I don't actually u sub. In this case, I'll do it just to show you what it looks like. So the lower limit of 0, that's for the variable x. So if I plug in 0 for x, u of 0 would be 0 squared plus 2, which is 2. So that would be my new lower limit after doing the u sub. What would be my new upper limit? This is a little funky. So the upper limit is t. You're going to plug that in for x. So u of t would be t squared plus 2. So that would be my new upper limit. So watch. Once I do the u sub, we have the limit. T goes to infinity. Integral from 2 to t squared plus 2. This x dx is gone. It's 1/2 du over x squared plus 2 squared. Who's that? X squared plus 2 right here. So then I have u squared in the denominator. Are we all right? It's looking like a hot mess to me. So let's do this. Limit t goes to infinity, 1/2 on the outside. Take those constants out. Look, you're going to feel better almost immediately. Instead of writing 1 over u squared du, I'm going to write this as u to the -2 du because I'm getting ready to integrate, and I know that helps me. What's our rule? We add 1 to the exponent, divide by the new exponent. So then we've got limit t goes to infinity, 1/2. This is going to be u to the negative first, and then I'm going to divide by -1. So I'll just put a big minus sign out here. And then evaluate this from 2 to t squared plus 2. Very good. Now this 1/2, you can just leave it on the outside. Don't get it involved. -1/2, stay away. So we've got limit t goes to infinity, -1/2. Now u to the negative first is 1 over u. So if I plug in my upper limit, t squared plus 2, it's going to be 1 over t squared plus 2 minus 1 over 2. Good? I always rewrite the terms that have negative exponents in the denominator as positive exponents when I'm going to take a limit, because it's going to help you evaluate it. Because watch, as t goes to infinity, this is getting very, very big. So a constant over something getting very, very big, where does that go? It goes to 0. And then that's so much easier to see and remember when you have it written in the denominator, instead of if this was t squared plus 2 to the negative first, it might take you, too many steps to imagine what's going on. All right. So what's left now? I've got negative 1/2 times 0 minus 1/2, another negative 1/2. Ooh, negative 1/2 times negative 1/2 is a positive 1/4. What do I care about 1/4? Only that it's a finite number, okay? Even if you get 1,042,000, that's a finite number. So we would reach the same conclusion. We would say that this is a convergent integral. And it converges to 1/4. All right. It is funky because when you think about it, when we define definite integrals from a to b of f of x dx, that represented the area underneath the curve, right? So you're like, what does this infinite limit mean? Well, you're summing up area forever. So technically, we're just looking at, are we adding small enough pieces that area converges or approaches a finite number, or does it blow up in the positive or negative direction? Anyways, let's move on to another example. Determine whether the integral is convergent or divergent. Evaluate it if it is convergent. So this is the last type that we talked about, where both the limits are negative infinity and positive infinity. So what you do is you split this bad boy up at your favorite number in between these two. And just make sure that the integrand is defined everywhere in between as well, which it is. 2 minus v to the 4th, that's a polynomial. So we have no domain issues. Usually, if it's up to me, I like to split it at 0 if I can, okay? But if pi is calling to you, or 7 or whatever, you live your life, okay? But the idea is we're going to break it up. The integral goes from negative infinity to infinity. You literally can pick anybody in the middle, say 0, and then now we're going to have 2 improper integrals. So here's how we rewrite it. First, we split it up, then we bring in the limits. So we'll go negative infinity to 0, 2 minus v to the 4th dv, plus 0 to infinity now, 2 minus v to the 4th dv. So just make sure where you left off the first integral is where you pick it up at the second one. Those need to match. And then we actually need 2 separate dummy variables. Now, I'm not going to get into it. It's really above the level of this course. But the limit as t goes to negative infinity, I'll use for this first improper integral. So this is going to go t to 0, 2 minus v to the 4th dv, plus, and then I do need a new dummy variable, limit as s goes to infinity, 0 to s, 2 minus v to the 4th dv. I always have a student who asks, like, can't I just make this negative t and do the same thing? No, I'm so sorry. It doesn't work that way. And if you go on to study higher level math, you'll see why, but just know that it's a no-no. Okay, so if one's going to positive infinity or one's going to negative infinity, they each need their own dummy variable for the limit. Okay, so how do we go from here? Well, we're going to have to make sure that both of these improper integrals converge. So you can try to work through them both at the same time, or you can just pick one, see what happens. So let's just work with this first one here since it's staring me in the face, this guy. So we're going to consider, so this is number 1, this is number 2, okay? The limit as t goes to negative infinity, integral from t to 0, 2 minus v to the 4th dv. Look at that. I gave you a relaxing polynomial to evaluate. I'm like, thank you, Professor V, but this will not be what I see on my homework. I know, but we're just getting into it. So we're going to do some relaxing ones. Antiderivative of 2 is 2v minus 1/5 v to the 5th, and then evaluate this from t to 0. So here we go. Limit t goes to negative infinity. 2 times 0 minus 1/5 times 0. That's the upper limit. Minus lower limit 2t minus 1/5 t to the 5th. So what's going on? This is all 0. And then I'm going to distribute this minus sign now. So now we'll have the limit as t goes to negative infinity of negative 2t plus 1/5 t to the 5th. Okay, very good. Now let's see. If t is going to negative infinity, negative 2 times negative infinity, where's that going? That's going to go to positive infinity. And then again, t is going to negative infinity. So if I raise it to an odd power, this is going to negative infinity times 1/5. That's not going to change the sign. It's still going to negative infinity. So I've got positive infinity plus negative infinity, which is the same as infinity minus infinity. Uh-oh. Why do I say uh-oh? Because that's an indeterminate form. Infinity minus infinity, indeterminate form. How many indeterminate forms are there? There are 7, like the deadly sins. I have a whole video on indeterminate forms. So if you forgot them, go back and watch it, but I'll just do a brief recap right now. The problem with infinity minus infinity is we don't know which one is dominating the situation. Is it this one? So will it go to positive infinity? Is it this one? Will it go to negative or 0 or some constant? We don't know. Infinity plus infinity is not indeterminate. They're not competing with each other. They're both getting big in the positive direction. Like we know where this is going. Or negative infinity minus infinity. That's not indeterminate. They're both going in the negative direction. If I have 2 of them, we're just getting there faster a little bit. But the problem is when they're not going the same way, when they're competing, infinity minus infinity, that's indeterminate. That's one of the 7. Okay, another thing to remember is indeterminate products. So for example, if you have infinity times infinity, that's not indeterminate. That's going to infinity. Or negative infinity times infinity. That's not a problem. That's going to negative infinity. You just look at the signs. Negative infinity times negative infinity. That goes to positive infinity. What's an indeterminate product? Infinity times 0. We don't know, again, which one is controlling or dominating in the limit. Is it the term that's blowing up or the term that's shrinking? Problematic. Okay, anyways, we don't need to get into like a whole side lecture on that. But what do we do with this limit? Well, a common little trick, no, you can't use L'Hopital's rule if you were saying that. Sorry, no, only for 0 over 0 or infinity over infinity. This is a polynomial. We don't even have a fraction. You can try to factor. Yes. So what I'm going to do, it might feel a little sneaky, guys, but go with it. Okay, I need more space, though. Please bear with. I'm going to take out a t. So this is the limit. T goes to negative infinity. Take out a t. And then I have negative 2 plus 1/5 t to the 4th. How did I know to take out a t? Experience. You might have to play around with it a little bit to find out what's going to work beautifully. But now look. So t is going to negative infinity. Okay, cool. So this goes to negative infinity. And then what's going on in here? Well, now I have negative infinity, but it's only raised to the 4th power. Ooh, that's even. So this is going to go to positive infinity. Positive infinity plus negative 2. Negative 2, I'm sorry, you don't really matter. When we're talking in terms of infinity, this is still going to positive infinity. Now this is not an indeterminate form. Negative infinity times positive infinity is going where? That's right, it's going to negative infinity. Very good. Now, alternatively, you can make the argument, right? This is just a polynomial. So the highest degree term controls the limit. Since this was going to negative infinity, it would be negative infinity. But I knew it's probably been a while since you guys have talked about indeterminate forms, so I thought it was important to revisit that topic. But for something like this, you could also say the highest degree term controls the limit on a polynomial. Okay, remember there were two improper integrals to evaluate. We only did one. Do we need to do the other one? No, because this one is divergent. Therefore, this OG integral has no chance of being convergent. Remember, in order for this to be convergent, both of these have to converge. So this guy, nope, sorry, was divergent. Therefore, we don't even have to waste our time doing the second one. Move on with your life, and we can say this is divergent. Had we gotten a finite number here, then we would have to go check, does the other one converge also? But basically, we lucked out, so we are done. Let's summarize. So stop here, please. Since one part is divergent, then we conclude the entire integral is divergent. Good? Fabulous. You hope this happens because it's less work. Okay, there's another type of improper integral. Are you ready? Yes. Definition of an improper integral of type 2. So if f is continuous on the interval from a to b, and notice we're including a but not b, because f is discontinuous at b, then the integral from a to b, f of x dx, is the limit as t approaches b from the left, integral from a to t, f of x dx, provided this limit exists as a finite number. So what's going on here? I don't see any infinities, no, in my limits of integration. The problem is the upper limit is some constant where the function, our integrand, is not defined. It's not continuous there. So we have to rewrite it again as a limit, replace that discontinuous little naughty upper limit with t usually, and then we take the limit as t approaches b from the left if it was the upper limit, okay? Similarly, if the lower limit is the problem child, is where the discontinuity is happening, then again, rewrite it, t approaches a from the right this time because it's the lower limit. I'll show you how to remember if it should be from the left or from the right. That always trips up my students. I got you, I know. And then as long as the limit exists as a finite number, then the improper integral is equal to this limit. Good? And then we use the same terminology for categorizing. So we say the improper integral from a to b of f of x dx is called convergent if the corresponding limit exists, and it's divergent if the limit doesn't exist. Okay? Now, again, sometimes the discontinuity can happen in the middle of the limits. So not at A or B, but somewhere in the middle, which is just the sneakiest type, let me tell you. So if F has a discontinuity at C, and C is between A and B, then what do? You split it up at C, and then you have to evaluate each of these separately. As long as they're convergent, then we say the sum of these two integrals is equal to the original improper integral. Okay, I got examples of all of these for you. I feel like these ones make me a little nervous when I was a student, because if they don't tell you that it's improper, you might not notice right off the bat. You'll get stuck in the middle and then realize it. But thankfully, these directions say, determine whether the integral is convergent or divergent. We only use that terminology for improper integrals. Evaluate it if it's convergent. So right off the bat, like when I'm a student and I'm reading this, I go, convergent or divergent, then that means it's an improper integral. I don't see any infinities, so the issue must be somewhere in these limits of integration, the integrand is not defined, right? And you go, oh yeah, see, I can totally tell this integrand is undefined or discontinuous at x equals 3. So which limit is the problem? This upper limit. So what do? We're going to rewrite it as a limit and replace 3 with a dummy variable t. But you have to figure out from which side we're approaching t. So just look at the limits of integration for the integral. It goes from 2 to 3. 3 is the problem child that we're replacing. How do you approach 3 on this interval? You can only approach it from the left side. You can't approach it from the right side, then you'd be out of bounds for the integral. We're coming from the left. So that means you're going to rewrite this as the limit as t approaches 3 from the left. That's so important that you put that minus sign there. Please don't forget it. Then we go 2 to t, very good. 1 over square root 3 minus x dx. Good? Okay. You guys are in Calc 2, so hopefully you can just do this integral in your head. If not, you might need to take some time to use sub, but I'm just going to get the ball rolling. So if you were to use sub and you let u equal 3 minus x, du would be negative dx. We're going to pick up a minus sign in the antiderivative. Also, this is all square root in the denominator, so it's to the negative 1/2. If I add 1 to the exponent, now it's to the positive 1/2. So my antiderivative is going to be negative 2 square root 3 minus x evaluated from 2 to t. Okay? Good, good, good. A lot of the times I do like to do the u sub in my head because like you saw in that other example, when we change the limits of integration, sometimes it gets messy. So if you can do it in your head, it just looks neater. Okay, let's evaluate it now at the upper and lower limits that we have. Right lim every step of the way, be a little math angel. Negative 2 square root 3 minus t minus, so I'll switch this to plus 2 square root 3 minus 2 is 1. Okay, great. So let's see. T is going to 3 from the left. Can I just plug in 3 for t and evaluate the limit? Sure, it's not undefined. It's not in the denominator or anywhere weird. So 3 minus 3, that's 0, times negative 2. This whole thing's going to 0. Plus 2 times square root of 1, that's just 2 times 1. So the limit equals 2. What do I care about that number? Only that it's finite. So that means this integral is convergent. That's it. How was that one? Favorite one of the lesson so far? Ooh, just you wait. I got more for you. I got more. Okay. Integral 0 to 1, 1 over 4x minus 1. I know. So this one, you might not right off the bat be like, oh, it's improper. But since I've kindly given you a heads up, it is. Look at the integrand. It's undefined when x is 1/4. So it's discontinuous. Ooh, at x equals 1/4. Is that an issue? Yes, because 0 to 1, that interval includes 1/4. So we have to split this up into 2. So we're going to rewrite this as integral 0 to 1/4, 1 over 4x minus 1 dx plus integral 1/4 to 1, 1 over 4x minus 1 dx. Now, these are the problem children, so we're going to replace them with dummy variables and rewrite it as a limit. So this is going to be the limit. T approaches 1/4 from which side? It has to be the left because look, the integral, we're evaluating it from 0 to 1/4, this first one. So how do you get to 1/4 from the left side? And then this is going to be 0 to t. Good. 1 over 4x minus 1 dx plus limit s goes to 1/4 from which side? Well, now this integral goes 1/4 to 1. How do you approach 1/4 from the right? So then put a plus sign here. S to 1, 1 over 4x minus 1 dx. okay? So yeah, technically we need to do both. Last time I picked the first one, so this time let's pick the second one just to spice things up. So I'm just going to consider this second guy here. So we'll look at the limit as s approaches 1/4 from the right, integral s to 1 over 4x minus 1 dx. Hopefully this is an easy antiderivative. You're just going to have ln, absolute value, all that stuff, but don't forget to put a 1/4 in the front. So we've got 1/4 ln, absolute value, 4x minus 1, evaluated from s to 1. Okay, looking good. So this is limit, s goes to 1/4 from the right. Don't put that in the like when you're evaluating the limits of integration. Put it outside. And then we have ln. What is this? 4 times 1 minus 1, ln of 3. It's already positive. I don't need to write absolute value. Minus ln, absolute value, 4s minus 1. Okay. So let's see what's going on. S is going to 1/4 from the right. This is just a constant, minding its own business. ln of 3. I don't care about you. S goes to 1/4 from the right. Okay, so 4 times 1/4 minus 1. Oh, shoot, that's 0. I know. So from the right is important. That means we're coming from numbers a little bit bigger than 1/4. So 4 times something a little bit bigger than 1/4 is a little bit bigger than 1. So something a little bit bigger than 1 minus 1. This is going to 0, but it's positive, right? Because the first term's a little bit bigger than the second term. So yes, again, you need that graph of ln. But you burned it in your brain from earlier, right? Because I told you to. Yes. So I'm drawing it again. I don't want you to imagine too much, but hopefully you're like, I got it, Professor V. I know what it looks like. Okay. Here's ln of x. Right here, the input is approaching 0 from the right. So you imagine you're walking on your graph and you're going to x equals 0 from the right side. Where's ln going? To negative infinity. Yep. So this whole term here is approaching negative infinity. Whew. So what does that mean for us? Let's see. I've got some number minus negative infinity. That's going to make this all go to positive infinity times 1/4. All that matters is this is positive. So it's going to stay positive. So this limit is positive infinity. What do I care? That it's not a finite number. So this is divergent. This improper integral is divergent. Do I need to go back and evaluate this one? No. Well, it doesn't matter if it's convergent or if it's divergent. Overall, this integral diverges. And don't get it all twisted. Just because this is positive infinity, if this goes to negative infinity, it doesn't mean anything. They do not cancel out in that way. No, no, no. They both have to approach positive or negative finite numbers in order for the integral to be convergent overall. I guess they could both be 0 as well. It just needs to be a finite number, okay? And in positive infinity and negative infinity do not cancel each other out. That's the big key. Okay, so we don't need to go back into the other one. Yay, I have one more for you. It's a little spicy because you're going to have to use more advanced integration techniques that you learned this semester. So here we go. Integral from 0 to 1, e to the 1 over x cubed dx. So where's the problem? What's making this integral improper? It's the 0 down below. Because then you would have 0 here, 1 over 0. Oh my God, what a mess. So we're going to rewrite this as the limit as s approaches 0 from the right. How do I know it's from the right? Because the integral goes from 0 to 1. So only way to get to 0 is from the right side. And then we're going to have s to 1 e to the 1 over x cubed dx. And you might say, Professor V, why did you use s this time instead of t? because I can see into the future. No, I wanted to save t because we're going to have to do more than one integration technique. We're going to first do a substitution and then do integration by parts. I know. So if you can't quite see what substitution to do, let me write out for you. This is the limit. S goes to 0 from the right. Integrals from s to 1. This is 1 over x squared times 1 over x. Isn't that the same thing as x cubed in the bottom? And then times e to the 1 over x dx. So maybe now you can see I'm going to make a substitution and let t equal 1 over x. Which is the same as x to the negative first. So dt would be negative 1 over x squared dx, which we kind of have, right? Here's 1 over x squared dx. So I just need to add an extra negative here. Okay, but notice we still have this extra 1 over x. We're going to have an extra t, which is why we're going to have to do by parts after. So this is limit s goes to 0 from the right. You got to still rewrite this every step of the way. Now my new limits, since t is 1 over x, my new limits here will be 1 over s and 1 over 1, which is 1. Beautiful. 1 over x squared dx, that's just negative dt. And then this 1 over x is t. And then I have e to the t dt, and don't forget your minus sign. Whew, are we okay? All right, good. Now it's time to do by parts because we still have this extra t left over and I can't get rid of it doing another substitution. This isn't a higher degree than this. So it's by parts time. That's why I saved u. So always let u be the polynomial, in this case negative t, and then dv is going to be e to the t dt. du is negative dt, and then v is e to the t. Good. So then we're still going to have here limit s goes to 0 from the right. The limits of integration don't change when you do by parts, which is nice. So then we're going to have u times v, so that's negative t e to the t. That gets evaluated from 1 over s to 1. Minus integral 1 over s to 1 v times du, which has an extra negative, so that'll switch to positive, e to the t dt. Good. All right, I'm going to hold off on evaluating this part until I do this antiderivative because they will all have the same limit, so we can just knock it out in one shot. So this is the limit. S goes to 0 from the right. I'm just going to write this as negative t e to the t. Antiderivative of e to the t, oh, so relaxing, plus e to the t from 1 over s to 1. Perfect. Okay, so now plug in upper limit minus lower limit. So this is limit. S goes to 0 from the right. Negative e to the first plus e to the first, that's the upper limit, minus lower limit. You know, poor planning on my part. I am out of space. Let's go here. Minus, now let me plug in 1 over s. So we'll have, well, now it's going to be negative 1 over s e to the 1 over s plus e to the 1 over s. Yes? Yes. So these guys just cancel out because this is negative e plus e. That's 0. So then we have, all right, so now we have the limit as s approaches 0 from the right. And then all of this is 0, so that's gone. Let's distribute this negative through. And we're going to have 1 over s times e to the 1 over s minus e to the 1 over s. And then to help us evaluate the limit, let's factor out e to the 1 over s. Because again, if we just tried it directly, it'll be problematic. So s approaches 0 from the right. Let's take out e to the 1 over s. And then I'm left with 1 over s minus 1. How are we doing? Okay, good. Now let's keep in mind, s is approaching 0 from the right. So 1 over s, that's going to approach positive infinity. If you need a review on infinite limits, I'll link a video in the description. So then e raised to something getting very, very large. This is getting very, very large, going to positive infinity. And then again, 1 over s. S is going to 0 from the right. That's going to positive infinity. Minus 1, that doesn't do anything. So this is still going to approach positive infinity. And I have infinity times infinity. That's not an indeterminate form. We know that that means the limit's going to be positive infinity. All right, what do I conclude from here? Well, since the limit is not a finite number, then we say this improper integral is divergent, or it diverges. So that concludes the video. Hope you enjoyed it and found it helpful. Like I said, I have lots of other videos on improper integrals, so those are all linked in the description. Don't forget to leave this video a thumbs up, subscribe if you haven't already, share it with your classmates, your neighbor, whoever might enjoy or benefit from this Calculus 2 video lecture. You can also follow me on Instagram and TikTok, Math with Professor V, and I'll be back sooner than later. Love you guys.